We're going to talk about the extreme value theorem, more generally, more properties of continuous functions. Let's first recap the three main theorems that we discussed last time. Let's say that f is a continuous function on a closed interval I from a to b. The first of our three theorems is the intermediate value theorem. Let's pick a number L that is between f of a and f of b. Then there exists a point P in the closed interval such that f of p equals L. That is, our continuous function f attains all of its intermediate values between f of a and f of b. The second is the boundedness theorem. There exists a lowercase m and an uppercase m such that f of x is greater than or equal to lowercase m and less than or equal to uppercase m. That is, a continuous function f is bounded. And the third is the extreme value theorem. There exists a number c in our closed interval such that f of x is less than or equal to f of c for all x in a closed interval I. That is, the function f attains its maximum value on the closed interval I. Similarly, there exists an element d from the interval such that f of x is greater than or equal to f of d for all x in the closed interval I. That is, the function f attains its minimum value on I. Today we're going to say a few more properties like these about continuous functions. Let's say that we have two continuous functions f and g on some closed interval I. Then the sum f plus g is also a continuous function. Let's explain why using an epsilon delta proof. As always, let epsilon, a positive number, be given, and let's pick a point P in our closed interval I. Well, since f is continuous at P, we can find a delta 1 such that, in absolute value, f of x minus f of p is less than epsilon over 2 whenever, in absolute value, x minus p is less than delta 1. Similarly, because g is continuous at P, we can find a delta 2 such that g of x minus g of p is less than epsilon over 2 whenever x minus p is less than delta 2. Let's choose delta to be larger than delta 1 and delta 2. Whenever x minus p is less than delta, we can use the triangle inequality to see f plus g evaluated at x minus f plus g evaluated at p in absolute value must be less than epsilon. Again, we've just used the triangle inequality here. So we conclude that our sum f plus g is indeed continuous at every point P in the closed interval. We can say the same property about the product of two functions. We'll explain why, again by using an epsilon delta proof. Let's say that a positive epsilon is given, and let's pick a point P in our closed interval. First, using the boundedness theorem, we can find m1 and m2 such that the absolute value of f of x is less than m1 and the absolute value of g of x is less than m2 for all x in the closed interval I. Now choose the delta 1 such that f of x minus f of p is less than epsilon over twice m2 whenever x minus p is less than delta 1. And we'll choose the delta 2 such that g of x minus g of p is less than epsilon over twice m1 whenever x minus p is less than delta 2. Now we'll choose delta to be larger than delta 1 and delta 2. Whenever x minus p is less than delta, we'll simply use the triangle inequality and a clever identity to see that f times g evaluated at x minus f times g evaluated at p will be less than epsilon. We can conclude now that the product f times g is continuous at any point P. Putting all of this together, let's denote this funny symbol C superscript 0, I comma f, to be the collection of all continuous functions f from a closed interval I to our complete ordered field F. This we call R. We've actually shown that R is a commutative ring. A commutative ring is just a fancy phrase for saying that the following 9 axioms are true. Essentially, we've already shown axioms F2 and F8. Actually, axioms just F1, closure. That is that the sum is a continuous function and the product is a continuous function. We're going to use all of this now to prove that every polynomial is a continuous function. We're actually going to prove this by induction on the degree n. Let's first take a look at the base case when n is equal to 1. In this case, then we can take a look at a continuous function. We'll prove that a linear function is a continuous function, namely f of x is a1x plus a0. Here, a1 could possibly be 0. We're only saying that we have a polynomial of degree at most 1. To this effect, let's choose a positive epsilon, and let's let delta be epsilon divided by the absolute value of a1 plus 1. Then we see that f of x minus f of p, we can write in terms of the absolute value of a1 times x minus p. Playing around with this, we see that this now is less than epsilon from the way we've chosen our delta. Hence, the first base case for p1 is true. Let's assume our inductive hypothesis that statement p sub n is true for some n equals m. And for the inductive step, let's take a look at n is m plus 1. Well, any polynomial of degree at most m plus 1 can be written in the form you see below, where we can actually write this as x times a polynomial of degree m plus some constant a0. We'll denote g of x as this polynomial x, h of x as this polynomial of degree m, and c of x as this constant. Well, both g of x and c of x are continuous because proposition p sub 1 is true. The polynomial h of x is continuous because by our inductive hypothesis, proposition p sub m is true. We know that the product g times h is continuous because we just proved this a little while ago. Similarly, the sum g times h plus c is continuous because the sum of two continuous functions is continuous. Hence, this proves that proposition p sub m plus 1 is also true. We've seen now lots and lots of examples that are continuous for every point p, such as polynomials. However, there are functions which are discontinuous for lots of points p. For example, we could maybe take the ratio of two polynomials. You can see, for example, that x divided by x minus 1 is discontinuous when p is equal to 1 because, indeed, it's not even defined at that point. You can see here on the screen the graph of a couple of different functions. On the left, you have the function x cubed minus 3x squared plus 2x, which is continuous. On the right, you have the ratio x divided by x minus 1, which is discontinuous. But now here's a really strange example. We're going to give an example of a function that's continuous at every point p. Let's define a function f such that f of x is 1 whenever x is a rational number, but f of x is 0 whenever x is irrational. We'll prove that f is discontinuous for every point p that's a real number. To this effect, let's choose an epsilon positive, but pick any epsilon you'd like strictly less than 1. Similarly, pick any point p in the real numbers. We're going to show that there does not exist a delta such that f of p minus f of x is less than epsilon whenever x minus p is less than delta. Let's assume by way of contradiction that such a delta actually does exist. Well, we've actually seen that the rationals and the irrationals are both dense in the real numbers. This means that if p is rational, we can find an irrational x such that x minus p is less than delta. And if p is irrational, we can find a rational x such that x minus p is less than delta. In either case, you'll see that f of x minus f of p is essentially 1 minus 0. So the absolute value, which is 1, will always be less than or equal to, greater than or equal to epsilon. But of course, this is our problem because we really wanted this difference, f of x minus f of p, to be greater than epsilon. So this is our contradiction. Thanks for watching.